Hello all. In this video we're going to take a look at a terrain example because that's closer to what we'll be working with in class that shows how A star would work on a grid world where we have variable costs in each grid cell. So we want to find a path from one grid cell to another grid cell, but the costs vary. And we've looked at least cost search in an earlier video. Here we're going to look at A star itself and just see how it looks. All right, we're ready to look at our example of A star. I will say this is a long set of slides. I'm not going to go through each one individually, but you can ask me for a copy of the slides if you would like to look at them more closely. All right, so this is the same grid world as we looked at with the least cost search. Notice there are weights, so there's some fairly expensive areas across the middle and some inexpensive areas around the outside. So what we want to see is, what does the search look like? Does it find the lower cost path, which actually is a very roundabout path, and to what extent does it search other possibilities as well? What we'd hope to see with A star is that it goes a little bit faster towards the goal than the least cost search, but this is somewhat of a difficult realm for it, so it may look a fair amount like least cost search. All right, so just a reminder, A star is going to keep the fringe set, the frontier set, organized by a cost that has two parts, the G part and the H part, and we're going to show both of those where we can. So as we show the priority queue, we'll show all three, and I'm going to draw a few steps of the search tree and show you the three scores as well. That's typical with A star because, as I mentioned in an earlier video, we need the old G scores to calculate new G scores. So we kind of have to keep around the G and the H values by themselves anyway. We are going to use the heuristic here that is the city block distance. It's a grid world. The trick is that what you'd look across is all the weights that we have. What is the lowest weight? And we're going to multiply the city block distance by that. But we have weights that are as low as 1. So city block distance will be 1 times the actual distance we have. So if you look at the start to the goal, the city block distance says that they are 1, 2, 3, 4, 5, 6 apart. So 6 steps is the minimum cost we could possibly have for any path if there were no weights involved. All right, so what we're going to do to start is just take this first starting point, starting state. We're going to add it to our priority queue. It's 3, 0, and we see that we have a G cost of 1 because in this terrain model, the weights are associated with the nodes rather than the edges in the graph. And so when you're at the start, you have a cost of 1 automatically. 6 was our heuristic distance to the goal, so we add those two together, and the cost that the priority queue is looking at is the 7. So it's always the F that the priority queue pays attention to. Just to show that, well, we'll just go on a step. We're going to pull that out of the priority queue. So 3, 0 comes out. We are now we've explored it, and we're going to add its neighbors to the queue. So we have the same neighbors as before, 2, 0, 3, 1, 4, 0. But you notice that things look a little different here. The G cost for 3, 1 is 3, but the H cost there for this state is 5. It's only 5 steps away, whereas 4, 0 and 2, 0 both have an increased H cost. So you can see that then the costs that we're actually organizing by are now different. 3, 1 looks more promising a little bit because it's headed toward the goal, so that's reducing the H cost and counteracting some of the cost of the actual move. The others look more expensive, mostly at this point because their H costs have increased. So the next time around, first, you can see here I've drawn out the search tree much as I did for the previous example. I'm just showing the G, H, and F costs. Remember, we look at the yellow ones, the leaves, and all we're looking at are the F costs. So for sure, this node right here, 3, 1, that's the one we're going to select next. And if you looked at the priority queue, that was also the one I drew on top in that picture. So we take 3, 1 out. It had a cost of 8. We look at its neighbors. 3, 0 has been explored, so we don't do anything with it. 2, 1, 3, 2, and 4, 1 are all new, and you can see that those get added appropriately. 3, 2 here has, again, a decreased H cost because we're moving directly toward the goal, but the G cost is going up quite a bit. And notice that we had the G cost here is 5 plus the previous G cost, which was 3. And so we get a total of 8. So other things are going to start bubbling up to the top because this direction is going to start hitting some expensive states. If we show this out as a tree, it just means we expand this node and we get its 3 children. Again, we look across all of the remaining. Ooh, I didn't color code this right. I apologize. This should be purple and this should be blue. I just forgot to color code them. So the remaining leaves, we'd look at their F costs. This 4, 0 has the lowest F cost. So that's where we would go next. All right. So 4, 0 looked like the most likely option at that moment. We pulled that out of the priority queue and we look at 4, 0's neighbors, which are 5, 0 and 4, 1. Notice 4, 1 was already in the priority queue. So what we need to do is to see, is it better to get to 4, 1 from 4, 0, or was it better to get to 4, 1 from 3, 1, which is what we had before. So that's what I'm writing about over on the right-hand side. We consider that 4, 1 is in the fringe. Going through 4, 0 gives us a cost of 9, which is less than what we had before. So we are going to change what's happening. So when I'm in this picture, what I'm drawing is that the little arrow is going to switch from pointing to 3, 1 to pointing to 4, 0 to indicate that that's a lower cost. We update the cost in the priority queue and we readjust the queue accordingly. When we draw the tree, it looks a little bit different, but it's the same idea. We notice that 4, 1 is here twice. We compare the two, and the one with the higher cost gets removed from the queue. That's a different way of conceiving of what is actually happening here. So one thing you can notice is that the cost didn't go up here. So this one, because the cost of the node itself was 1, we kind of keep in that total of 9. And so this node, even though it's most recently generated, is actually going to be selected next. All right, so we select 4 with cost 9. 4, 1 that is, and we look at its neighbors 5, 1 and 4, 2, and they slot in here accordingly. Notice that 4, 2 is still looking pretty good. It has it's only 5 away, and its cost has gone up to 5, so it's still in the running. And 5, 1 is down here at the bottom because it's a little further away and its costs are going up accordingly, but we haven't really hit any of the really expensive ones yet. All right, I'm going to speed up and not quite go through everything in as excruciating a detail, but I'll show you one last tree. So here we expand 4, 1, we get these 2 nodes. And again, the ones that are left in yellow, those are the ones we're considering. And so we've got 2, 0 and 4, 2 are actually our 2 points that look most promising. So if I go back 1, you can see that's 2, 0 here and 4, 2. And it kind of makes sense. This one is promising because its cost is low and it's still close to the right row. This one is closer to the goal, so it looks more promising as well. All right, I'm not going to keep drawing the tree after this. They just get really big and unwieldy, and they're easier to do by hand than they are on slides. So we're just going to kind of keep working through these things. So 4, 0 happens. We have a neighbor 2, 0 happens, and it has a neighbor 2, 1 that was already in the tree, but when we look at it, it's actually more expensive to go through 2, 0, so we don't make any changes to that one, and we add 1, 0 as a new node. It's relatively expensive because we're getting the distance, the heuristic distance is going up quite rapidly. We then go to try 4-2. 3-2 is a neighbor that was already in the fringe, but we don't update it because it's still more expensive. And notice that 5-2 is a neighbor that now has a really high cost because we're starting to hit those more expensive cells in the grid. So that's dropping all the way to the bottom of the priority queue. All right, so we do 2-1, and I'm just going to kind of step through these. So you can see that it's spreading out. It looks a lot more like maybe least cost search than you might expect. And that's mostly just because it wants to go straight toward the goal, but these have now gotten expensive. So it's exploring more in both the top and the bottom corners to try to see if there's any way around that expense. And here it's going to start to find what we're looking for. So it's going to start to find that less expensive path along the top, but the costs are going up by 2, so eventually it will come back and explore some other things in other parts of the map. And you can see that just by looking at the locations. It's going to look at 4-3 next, and then it comes up to 1-2 and 0-2. And then it's actually going to come back down here unless it gets superseded. It'll come back down and explore some of these lower points. So, and it actually does. And here it really starts to move straight toward the goal because everything else is getting more expensive. The costs have gone up for all of these, a lot of these neighbors. 5-2 is the only one that's left that doesn't have a particularly high cost. And so at some point we do come back and we try to fill in some of those other alternatives, but they just aren't playing out, and we end up finding the goal. So where you see A* differing from least cost search is that when it got to this point, it really was able to hone in and explore a lot of this space without too much going back. It has less going back to explore other places because it's taking into account that the ones down in this corner are just a lot further from the goal than the ones up in this corner. All right, I encourage you to work through some small examples yourself, and we'll have some software that the Maze Planner program that I had a video about before that we will also use to take a look at A* and see how it runs. I will see you in a little bit.